We're surrounded by these incredible devices every single day, right? They think, they calculate, they connect us to the world. But have you ever really stopped to wonder what's actually doing all that thinking? Well, in this explainer, we're going to pop the hood and take a look at the one component that powers our entire digital world, the CPU. So let's start with a really simple question. You tap your phone screen, you clip your mouse. What is actually going on inside that machine to make it all work? I mean, what's doing the real thinking here? Well, the answer is this small, pretty unassuming looking chip right here. Yeah, amongst all the fans and the drives and the circuit boards, it's the central processing unit, the CPU, that's the real brain of the whole operation. It's the engine that processes every single instruction you throw it at. And honestly, that's not an exaggeration at all. Let's put it this way. Without a CPU, a computer is just a lifeless box of parts, nothing more. This one little component is what brings the entire machine to life. Okay, so if it's the brain, how does it actually think? To really get that, we need to peel back a layer and look at its fundamental design. So pretty much every modern computer you've ever used is based on something called the von Neumann architecture. Now, the core idea is actually pretty simple, but it was totally revolutionary. It says that the computer's instructions, its to-do list, and the data it needs to work with are stored in the same memory. This is huge because it means the computer can treat its own instructions as just more data, which is what lets it be reprogrammed for pretty much any task you can imagine. So, if we break the CPU down even further, you'll find it has three main parts working together. First, you've got the control unit, or CU. Think of it as the project manager, just directing the flow of all the information and making sure everyone's doing their job. Then there's the arithmetic and logic unit, the ALU. This is the calculator, the mathematician of the group. It handles all the addition, subtraction, and logical comparisons. And finally, you have the memory unit. This is like the CPU's own super-fast, short-term memory, a scratch pad for holding whatever it's working on right this second. Okay, so how do all these components actually work together? Well, they follow this relentless four-step dance. This cycle is the absolute core of how a CPU processes every single command you give it. It's called the fetch, decode, execute, store cycle, and it goes like this. First, the CPU fetches an instruction from memory. Then, the control unit decodes it, figuring out what on earth it's supposed to do. Next, the ALU executes the command. It does the actual math or logic. And finally, the result gets stored back into a register or memory. Fetch, decode, execute, store. It just does this over and over and over again. And here's the part that's just, well, it's mind-boggling. This four-step cycle doesn't happen a few times a second, not even a million times a second. Modern CPUs repeat this process billions of times, every single second. Just let that sink in for a moment. Now, obviously, the CPU in your phone today is light years ahead of those early microprocessors. So how in the world did we get from there to here? Let's take a look at how these digital brains evolved to get so much smarter and so much faster. One of the biggest game changers was the jump from single-core to multi-core processors. So think of a single-core CPU like having just one chef in a giant kitchen. They can only cook one dish at a time, right? But a multi-core CPU? That's like having a whole team of chefs in the kitchen. Each core is basically its own mini CPU, which lets the processor juggle multiple tasks at the same time. That's exactly why you can stream music, have a dozen browser tabs open, and run a virus scan all at once without your computer melting. But hold on, it's not just about adding more chefs to the kitchen. CPUs got faster in other really clever ways too. You have faster clock speeds, measured in gigahertz, which just means how many of those fetch, decode, execute cycles it can run per second. Then there's bigger cache. That's like giving each chef a bigger countertop to work on so they don't have to keep running to the pantry or the slower RAM for ingredients. And then you have something called pipelining, which is super cool. It's like an assembly line where the CPU starts working on the next instruction before the current one is even totally finished. I mean, the pace of this change has been absolutely incredible. It all kicked off with the invention of the transistor back in 1947. Just a little over 2 decades later, in 1971, Intel managed to pack a bunch of them onto a single chip, the famous Intel 4004. Fast forward to 2005, and AMD brings the first consumer dual-core processor to market, which made multitasking a reality for all of us. And today? Well, today we have chips like the Core i9 that deliver a kind of power that was just science fiction not that long ago. So this incredible evolution, this shrinking in size while exploding in power, means that CPUs aren't just in giant mainframe computers anymore. Nope, they are quite literally everywhere. Let's start with the obvious one, the computer you're probably watching this on right now. The CPU in there is the master conductor, running your operating system, your web browser, every single app you open. It really is the engine of your daily digital life. And what about that smartphone in your pocket? The very same principles apply. Mobile CPUs are specially designed to be super power efficient, to save battery, but they are still ridiculously powerful brains that handle everything from your apps to your video calls on the go. But let's think even bigger. On a massive scale, the entire internet basically runs on CPUs. Inside these huge data centers, there are just racks and racks of servers, each packed with powerful processors. They're the ones handling the millions of requests every second that power websites like Google and YouTube. But for all their amazing power, CPUs aren't perfect. There are trade-offs. See, their biggest strength is that they're a jack of all trades. They're super versatile. But that versatility comes at a cost. They get really hot and suck up a lot of power. That's why your laptop has a fan buzzing away. And while they can do almost anything, they aren't the absolute best at everything. For really specialized tasks, like rendering the graphics in a video game, that's where a different kind of brain, the GPU, often steps in and takes the lead. So when you think about it, we've gone from a simple chip that could barely do addition to these multi-core giants that are now powering artificial intelligence. The journey of the CPU has been nothing short of revolutionary. And it really makes you wonder, right? As we keep pushing the absolute limits of physics and engineering, what incredible new frontiers will the computational brains of tomorrow be able to think of?